Everyone, my name is Anurag, Associate Professor in EC Department of BVC Engineering College, Vadalrevu, Andhra Pradesh. So, coming to the today's lecture, we are going to discuss about pulse time modulation. So, as in the concept of an pulse modulation techniques, in the previous session we have seen about pulse amplitude modulation and how we are going to generate this PAM wave and demodulate a message signal from the PAM wave, and also the advantages and disadvantages of this PAM. Next is the concept of PWM or PTM or PDM. So next is pulse time modulation. It is also called as a pulse width modulation or pulse duration modulation. As we know that in pulse modulation techniques, any one of the characteristic of a carrier wave or pulsated wave is going to be vary in accordance with the instantaneous values of the message signal. In the previous case, we have changed the characteristic called as an amplitude, and now we are going to identify how the width or time duration of an pulse, that is on time, is going to be varied with respect to a message signal, is called as a pulse duration modulation or pulse width modulation. So in this, the remaining characteristics called amplitude and phase are going to be kept constant, or amplitude and position are going to be kept constant. The width of the pulse is going to be varied proportional to the amplitude of the message signal at that particular sample, because we are going to handle during the pulse sample. So when the pulse signal is present at that point of instant, depending upon the amplitude of the message signal, the width of the pulse may increase or decrease. That is what the main objective of this pulse width modulation. It is also called as an pulse time modulation and pulse duration modulation. So the main advantage of this pulse time modulation is here the amplitude of the pulse does not carry any information. So the effect of noise on the pulse signal is very less, so that it can be highly immune to noise. How we are going to generate this pulse width modulated signal? There are two methods for generation of this pulse width modulated signal. One is indirect method, second one is direct method. So coming to this pulse width modulation generation techniques, so it can be simply represented as a comparator which is going to have two inputs. One is the non-inverting terminal of an comparator will be provided with an input signal, and the inverting terminal of a converter is going to be provided with a sawtooth waveform, so that the output of this comparator will produce this PWM output. So here the generation of PWM, and also the next stage of PWM is nothing but an PPM, which can be generated by using a single comparator is shown here. So here the plus sign of a comparator is provided with x of t, which is my message signal, and negative sign of an comparator is provided with input sawtooth generator. Here we can see in the graph the sawtooth waveform and message signal x of t. So here in the first graph below, the circuit diagram shows that x of t message signal is overlapped on sawtooth waveform, and the below waveform is nothing but an PWM waveform or P, and the last one is my PPM waveform. So first of all, we can identify how a PWM waveform is being generated. So if you see the first starting cycle of a sawtooth waveform, The starting edge or the starting point from where the sawtooth waveform is negative to 1, it started, my pulse signal is going to be on, and it maintains a constant amplitude value until it meets the message signal, so that it will be the on time and the remaining time will be off until unless the starting of the next cycle. A sawtooth waveform consisting of a ramp signal, and suddenly it is going to be fall to the zero value. So during that cycle duration, so until unless the starting of the pulse sawtooth waveform, at that point only it is going to start my PWM waveform and maintains a constant amplitude until unless it finds the message signal. Once it finds the message signal, again the pulse width modulated signal will become 0, and similarly the same process goes on for the remaining cycle, which we can see in the second waveform. So if we see here, if the input amplitude x of t is high, the on time of the pulse signal or the on time of the pulse width modulated signal is more. And similarly, if the amplitude of the message signal is minimum, the on time is minimum. So for every pulse cycle is constant. It only varies with the on time and off time. And once this PWM waveform is given to a differentiator, it gives the spikes, and whenever or wherever the spike is present, if we place a pulse with constant amplitude and width, which produces my ppm, that is what the next technique we can see later on. So this is how my PWM waveform can be generated simply using a single comparator. So here, so this is what the explanation of the previous slide. So the non-inverting input of the comparator is fed with an input signal, and the inverting signal is given with the sawtooth waveform. This comparator compares the two signals and produces PWM as an output. The output is high only when the instantaneous value of x of t is greater than the sawtooth waveform. And during the rising edge of the PWM signal occurs, and fixed time period and trailing edge depends upon the amplitude of the message signal. So the sawtooth waveform is reversible. So the amplitude of PWM is positive of the comparator, shows A being the same of the pulses. So this is what the simple explanation of the previous circuit diagram is. Types of modulation techniques. And these PWM modulated techniques can be of three types depending upon the point of reference we are going to consider. So if we are making the leading edge of the pulse is constant, that is the trailing edge varies according to the message signal. That is what the first type, which you can see in the waveform A. The starting of the pulse signal is constant, and the trailing edge depends upon the message signal. And similarly, second case is the trailing edge of the pulse is kept constant, but the leading edge is going to be varied according to the message signal. And in the third case, both the trailing edge and leading edge are kept constant. Sorry, the center of the pulse is kept constant. The leading edge and trailing edge will be varied according to the message signal. These are what the three different types of an PWM signals. Next is indirect method of generation of an PWM. So in this indirect method, so in the previous case directly we have make use of message signal and then pulsated signal, so which generates my PWM waveform. That is what the direct method. In this indirect method, first of all we are going to generate a PAM signal, and with the help of this PAM signal I am going to generate my PWM method, PWM signal. It is called indirect method of generation of PWM. So if we see the block diagram here, the input x of t and the pulse signal s of t are given to an PAM generator, and The same pulse signal is also given to a ramp generator, which generates a corresponding ramp depending upon the width of the pulse signals. That means here the output ramp generator is going to produce a ramp signal of constant ramp for each and every cycle of a pulse signal. Because you see here S of t is a carrier signal which is going to have a constant on time and off time for every pulsated cycle, so that the ramp signal will be constant, and the generated ramp signal is given to an summer which takes PAM output as second input, and this summer adds both the signals PAM signal and ramp generator output, and the output of this summer is going to be given to a Smith trigger which generates a width of rectangular pulses called PWM waveform. So if the amplitude is high, width will be more. So on the ramp signal, these PM signals will be present. If the amplitude of this PM signal is more, the width will be more. If the amplitude of this PM is less, the width will be less. So here the output of the summer is generally given to an clipper in order to maintain some reference values. So this is how a PWM can be generated using the indirect method. That is about generation of PWM waveforms. Next is demodulation of PWM signals or PWM detector. So the input signal will be the PWM signal. So here we can see the output waveforms of a demodulated signals here. The input signal is in PWM signals, and these PWM signals are given to necessary blocks which are shown in the PWM detector block diagram. So here PWM detector is going to make use of ramp generator and synchronization pulse generators. So there should be some synchronizing pulses should be required in order to identify the reference value so that it can generate my demodulated signal at the output stage. So PWM signal is given to a ramp signal, and similarly it is also provided to the synchronizing pulses, so that depending upon the type of an PWM waveform, whether it is having an standard leading edge or constant leading edge or constant trailing edge or constant center point of this pulse signal, depending upon that a synchronous pulses will be generated, and these synchronous pulses are of constant height and constant width, and depending upon the width of this PWM waveform, this ramp generator is going to produce corresponding ramp signals of so and so height. If the width is more, ramp will be high, ramp will be more. If the width is less, ramp will be less, which can be seen in the third waveform of an output demodulated waves. So here the output in the output demodulated waves, first is my PWM waveform, which is given to both the ramp signal and synchronous pulse generators. So depending upon the type of an PWM waveform, first the synchronous pulses will be generated, which is shown in the second waveform, and the ramp generator is going to produce corresponding ramp signals, which is shown in the waveform number 3. And these outputs 2 and 3 are given to an adder, which produces a signal which is shown in the signal 4, and this adder signal output is given to a level shifter so as to identify only the pulses of various amplitudes at the output state. So level shifter is just a marker. It is going to mark a particular level, so that whenever this level shifter or the output with this particular marker is given to a rectifier, the rectifier is going to keep or is going to maintain the desired signal and delete the remaining signals which are shown in the 4 and 5, or the output of an not 4 and 5, 5 and 6. So the output with a level shifter is shown in the waveform number 5, and when this output is given to a rectifier, it is going to keep all the values above this level and it is going to eliminate all the signals which are present below this level, which is shown in the figure number 6. And finally, this output is given to a low pass filter, same as in the case of an PAM demodulation. So here this PWM is converted into PAM, and that PAM is converted into a message signal using a low pass filter. We have seen in the PAM demodulation how it is going to identify. If you want to identify, if you want to know how PAM signal is converted to message signal, just go through the previous session shown in the PAM demodulation. And final, the output of a low pass filter is my demodulated signals. This is what how a PWM can be detector can be implemented. Next session we can see about pulse position modulation. Thank you.